And those bits define the apple. Its shape, its color, its texture, its very existence can be defined as bits of information.
Josiah Willard Gibbs at Yale, they actually discovered the fundamental formula that described information. And they didn't describe it in terms of bits. They discovered that formula because they were looking at how atoms move around. And they wanted to quantify this funky stuff called entropy. Now, entropy was at that time known as a quantity that gummed up the works of heat engines, of steam engines, and kept them from doing the amount of work you'd want them to do. But phrased in modern terms, what Maxwell, Boltzmann, and Gibbs discovered was that entropy is actually information. It's bits. So these atoms, as they move around, they carry bits of information with them. And every time two atoms collide, those bits flip. So in fact, not only does information have everything to do with physics, but physicists actually discovered it to begin with.
And it can also be what, now we have light that's carrying information, like fiber optics, so it could be a quantity of light as well.
Yeah, so if you want to see, if we're looking at how the information processing revolution came about, it's because scientists and engineers figured, oh, everything's already got this information associated with it, let's use it. You know, a particle of light, a photon, it can have a bit of information, like if it's wiggling back and forth like this. So if I take, my Ray-Bans, I put it like this, photon wiggling back and forth like that, you can call that a 0. Photon wiggling back and forth like this, Ray-Bans like that, you can call it a 1. So all these, particles, physical entities have information associated with them. And when we build things like quantum computers, all we're doing is just taking advantage of that.
So let me turn to Chris Fuchs from Perimeter Institute. Can you give me an example of how the laws of physics allow us to do things with information?
Here's a lovely example, something called quantum cryptography. The task that's set in front of two people, Alice and Bob, is that they'd like to share a secret. They'd like to communicate to each other privately. In the classical world, where there was no connection, at least no seen connection between physics and information, when they would send messages back and forth between each other, somebody could gather information and it has no effect on the carriers of the information. Well, in the quantum world, there seems to be a deep connection between the properties of things and the information that one can get about them. So, for instance, if you get information about something, it changes the system in the process. This leaves a trace. Alice and Bob can see this trace, and they can learn whether someone has listened in on their conversations. Well, in the quantum world, there seems to be a deep connection between the properties of things and the information that one can get about them. So, for instance, if you get information about something, it changes the system in the process. This leaves a trace. Alice and Bob can see this trace, and they can learn whether someone has listened in on their conversations.
If you had a bathtub full of hot water, what information do you need to know in order to know whether to get into that bathtub or not? Well, you need to know its temperature, you may need to know its volume, to know if there's enough water there, and so forth. But that's a very limited amount of information. There's an enormous amount of information stored in the position and velocity of every single molecule in the water. If you really want to know exactly what's going to happen next, you need to know the position and velocity of every single molecule in that water. So there's an enormous amount of hidden information that you don't ordinarily see when you look at the bathtub full of water. That hidden information, the information that you can't see, is what's called entropy.
This right here is a point. That is information. It exists, therefore it's information. As this moves this way at the Big Bang, that creates information, information here as it moves. It's projecting information from here to here. And then from here, this way, here's your time, your relative time, right there. There's your relative time. Alright. So this is 1D relative time, plus 1D length right here. Now, right here you got the Big Bang. This dot by itself is information. There's no 2 points right here. This is your second point right here. This is your length. This is your motion. This is your velocity. Okay. And this is your also your dimensions and your kinetic energy. Kinetic is motion. Right here. At the Big Bang, it expanded, and this is what this is right here. This represents this right here. These are your waves. So let's just say that this is going like that. Alright. This happened here. Information. Anytime something moves, it's creating information about its existence, about its physical properties. So from here to here, that's speed, and from here to here and back, that's velocity. Zero velocity. So even though it moves, it still requires 2 points, even with zero velocity. It requires from here to here and back. Alright, imagine a piston or something. Just for example, something vibrating. So motion, here you have motion, expansion, kinetic energy, and information, and this is what creates your spatial dimensions. So from here, here's your time right here. See that here? Here's your 1D time. 1D time, this is relative time. This is after the Big Bang. It creates 1D time plus 1D length. 1D length plus 1D time equals 2D waves. That creates a 2D wave energy. Alright? Let me see if I could get this clear. To the waves. Now within, so let's just say the Big Bang's here, just for now. The Big Bang occurred here and it expanded. The waves expanded. And this creates your positive and your negative charges right here, your electric magnetic field. Alright? And inside, within the waves, is creating information as it moves. And remember, the only reason you could have information here is because at that one point, remember, the single point right here, let's say right here, that is information. It could be anything you want. That's a single point. There isn't any motion. There's no motion from here to here. That's 2 points. There's time, relative time. There's dimensions, expansion of the Big Bang, and kinetic energy. It's all right in there. 2 points. Now, some people try to create a grid, for example, right here. This right here is a point. This is information. In order to create a grid, in order to place coordinates, you know, like longitude and latitude and all that, or vectors. Here, this is a grid right here. See, 1, 2. There's a dimension. But in order to create a grid, you require dimensions already set from here to here. Alright? And then what they try to do is try to make you believe that you could place here a coordinate right here in the center, right here, anywhere, right there. See, for example, right there. Right? But you can't even have that without a dimension here. A dimensional grid. This right here, by itself, represented right here, just say this right there, again, that is information. Is right here. Space-time is all these waves creating space by using time. This is called general relativity. Right here you also have your gravity in here. It's after the Big Bang. And then you have over here, you have your black holes right here. You can't have this unless you have space-time already in place. Because black holes require mass in order to exist.